So good evening, everyone. I'm Priyanka. I have Aitan and Daniel with me, and our presentation topic is Hadoop MapReduce system. So I'd like to start with the a definition of Hadoop. Daniel, next, please. So it is an open source framework that was created to make it easier to work with the big data. It provides a method to access and process the data, which is distributed among multiple clusters and computers, and also it manages computing and network resources that are involved in the processing of the data. Next, please. So this is history of Hadoop, and I'll just quickly go over it. So in 2002, internet researchers wanted a better search engine, and that is when Doug Cutting and Mike Caffarella decided to work on the better search engine, and they called their project as a nudge. And while working on it, they came across a problem of sorting very large files which were being generated because of web crawling and indexing processes. So that is when Google in 2004 published their paper on MapReduce, and which had the solution of processing the large data set. So Doug and Mike, they implemented this solution, uh, uh, Google's GFS and MapReduce as an open source in Apache Nudge project. And in 2007, Hadoop, Yahoo successfully tested the Hadoop on 10,000 node cluster and started using it. So in January 2008, Yahoo released the Hadoop as open source project. Next, please. So there are few misconceptions about Hadoop, which I would like to address. People often use Hadoop interchangeably with big data, but actually Hadoop is framework to work with the big data and not big data itself. Hadoop, it is part of big data ecosystem. Next, please. So Hadoop, it consists of four main modules: HDFS, Yarn, MapReduce, and Hadoop. So I'll be focusing on the MapReduce section, and Item later will complete all these modules in detail. So next, please. MapReduce, it is a programming model that allows us to perform parallel and distributed processing on huge data sets or on big data, and it consists of two tasks, which are map and reduce. Uh, Next, please. In the map job, a block of data is read and processed to produce a key value pair as an intermediate output, and this output is then provided to the reducer. So next, please. So the reduced job receives this key value pair from multiple map jobs and aggregates those intermediate data tuples into a smaller set of tuples or key value pair, which is the final output. And next, please. So here in this slide, I have example of a MapReduce work count process. So we have an input file and we need to count the words or number of words, count the word in this input file. So or occurrence of each word in this file. So first we will divide the input file into three splits as shown in the figure, and this will distribute the work among all three map nodes here. And then we tokenize the words in each of the mapper and give a value 1 to each of the tokens or words. So we have a list of key value pair, and uh, so now the first line is a deer, beer, and river. So we have three key value pairs. So deer has value deer with value 1, beer with value 1, and river with value 1. The mapping process, it remains same all for all the map nodes, and after the mapper phase, a partitioning process takes place where sorting and shuffling happens so that all the tuples with same key are sent to the corresponding reducer. So after the sorting and shuffling phase, each reducer will have unique key and a list of value corresponding to that very key. So for example, beer will have values 1 and 1, car will have value 1, 1, 1. So now each reducer counts the values which are present in that list value, and as shown in the figure, reducer gets a list of values which is 1 and 1, and for the key beer, and then it counts the number of ones in that list and gives the final output as beer with value 2. So finally, all the output key value pairs are collected in the output file, and we get the count of each word. Next, please. So, so I have just covered installation of the Hadoop. Here, um, I have steps to install a single pseudo distributed Hadoop cluster on Windows. So you need to have a Java 1.8 on your machine for installing Hadoop, and then you can download the Hadoop. After download, you can create the two environment variables and provide the path of bin folder of Hadoop in one variable and the Java bin folder in the another environment variable. And then we need to edit some files located in the Hadoop directory. These file names are core site, Hadoop environment, HDFS site, and MapReduce site. Uh, so Hadoop needs Windows OS specific files, which might not come with the default download of the Hadoop. So we need to custom include these files in the bin folder. And installation of Hadoop over Mac and Linux is fairly similar. So to install it on the Mac and Linux steps, um, so we need to confirm which version of Java we are using, and we need to make sure that Hadoop is supporting that version. And then you can install Hadoop using brew command. And we need to perform some configuration changes on the file core site, Hadoop environment, HDFS site, and MapReduce site. And then you can go to the bin folder to start and stop the Hadoop services. So now Aitan would continue with the system architecture in detail.
Okay. So now that we've gone over a brief introduction of the Hadoop MapReduce system, we're going to go ahead and transition over to the system architecture side, where we're going to talk about three main components in general: the application layer, which is Hadoop MapReduce itself; the resource management layer, which is Hadoop Yarn; and the storage layer, which is Hadoop HDFS. Next slide. Thanks. Okay, as a recap, the MapReduce ecosystem as a whole works basically in two phases: a mapper and a reducer. The map task primarily deals with the splitting and mapping of the data, while the reducer will have tasks to shuffle and reduce the data. The entire process of MapReduce is regarded as a software framework that is used to process large amounts of data. And by default, the programs of MapReduce are built to be parallel in nature. And similarly, they work with hardware in a parallel manner as well, as resources can be distributed across a cluster or a collective group of machines that can work together to accomplish the specific data processing task. Next slide. So now we have Hadoop Yarn. With Hadoop having a distributed nature where it can work across several machines, there came across an issue where we needed something that can actually keep track and provision resources on an ongoing basis. So here comes Yarn, or what it stands for really is yet another resource negotiator. And Yarn actually sits right in between the application layer, so Hadoop MapReduce, and the storage layer of the HDF, which is HDFS. And it functions really to monitor and schedule the processing operations in the individual nodes. It works with a centralized resource manager, as seen on the right, where it communicates everything through the resource manager, and it helps with coordination. And lastly, Yarn can help decentralizing the execution and monitoring of the jobs by sort of splitting up its responsibilities into other components, which these components fall under the resource manager, the node manager, and the application master. Starting with the resource manager, this functions as a global manager. So for the entire cluster, that will accept job submissions, will help scheduling the jobs and allocate resources to them. The node manager itself is installed on each node, and it will monitor and report the status of each node to the resource manager. And finally, the application master is created actually for each application and will help negotiate resources and work alongside the node manager to help monitor and execute the tasks as well. Next slide. Okay, so we saw a brief diagram of what the resource manager does, but if we take another level down and look at it in more depth, it's actually an agglomeration of functions that serves to accomplish several tasks or several services. And if we break it down into its further components, um, we'll start with client services. So it has a client service, which is essentially the interface to the resource manager, and it'll handle all remote procedure communications or RPC communications, like application submission, termination, queue information, and even cluster statistics. The administration service or admin service is made to have a separate interface through which all administrative commands will run through, or all administrative operations can be executed, like refreshing the nodes and even configuration information to avoid conflicts between regular commands and administrative commands. Moving into node services, we can start with, no, previous slide, one after. Yeah, you can stay on this one. So for node services, we're starting with the resource tracker. And the resource tracker will respond to communications. It will help register new nodes and will accept and reject requests on an ongoing basis and forward anything as needed to the Yarn scheduler. We also have a liveliness monitor that falls under node services, and this will essentially have the primary duty of keeping track of which nodes are alive and healthy, or in that matter, unhealthy if they go down. And we also have a list manager, which will keep track of all the valid and invalid nodes as defined in the configuration files. And this is especially useful in larger clusters, where if we want to update a node or remove a node from our workload, we can easily do so with this list manager. And similarly to the node services, we have application specific services where we have a application master um, that can help communicate between all of the application masters itself and keep track of all the healthy and unhealthy application masters in the cluster. Uh, we also have the liveliness monitor, which will do the same thing as the node manager liveliness monitor and keep track of which are alive and responsive to service. For core services, we have an application manager, which will maintain all of the information from the applications and also cache data to serve the web interface of Hadoop or Hadoop MapReduce. We also have an ACL manager, which is generally responsible for managing and authorizing requests from the client and admin side. So which requests are going to be approved or not for certain tasks. And we also have the master launcher or application master launcher, which is responsible just for launching these application masters and cleaning them up also when we are done with the application upon termination. And lastly, for core services, we have a scheduler, and this scheduler allocates resources based on the requirements like memory and disk usage to the running applications. And the final component of the resource manager is security services. In general, all of these security services are simply in charge of managing tokens and secret keys that are used to authenticate requests on the different interfaces of the system. Next slide. So similar to what we saw previously in the resource manager, the node manager is also a collection of functions and services that work together to help support the main functionality, which generally fall under two main things. container launching, and log aggregation. The node manager will launch and manage all of the containers that are on a given node and help execute the tasks that come from the application master. And by default, it is also responsible to keep copies of the resources and isolate the directories or working directories in the container itself so that it's functional, and maintain logs of the associated containers. Next slide. So as a summary of what we've went through for Yarn, the main features that it helps provide for the Hadoop system or Hadoop ecosystem is multi-tenancy. So we can have, as an analogy, if we have the several individuals occupying the same apartment complex, we can think of nodes that reside in the cluster in a similar fashion, and they all share and use resources accordingly. So that's the multi-tenancy um, feature or aspect. It also helps in utilizing a central point of communication. And this central point of communication allows us to use computing resources um, at a centralized location, which helps with cluster utilization, all from a central point. And we also have scalability. So Yarn allows Hadoop itself to be scalable regardless of the number of nodes in the cluster, either if we increase or decrease them based on the application requirements. As such, it can scale due to the resource trackers that it provides and can provision and decommission resources all through that manager. And lastly, we have compatibility, as it maintains the same exact structure no matter how many times we use it across a wide variety of applications. Next slide. Okay, so now we have another main component of Hadoop, possibly the most important one, is HDFS, or the Hadoop Distributed File System. And this is the storage component of Hadoop. All the data that is stored on Hadoop is stored in a distributed manner, which can be across multiple devices or in a cluster which has multiple machines. And the reason behind this storage methodology is that it is found to be more cost effective and easier to manage huge data files, as the case is with big data, without the need of worrying about singular points of failure, which can be storing all of your data on a single machine. And if it goes down, everything is lost, essentially. So to make this work, we have a master slave architecture that is used in Hadoop, where the primary node, or the master, which is called the name node, manages the file system along with all of the file system access and operations, and will also help with metadata and regulating different commands such as opening, closing, and renaming. The slave nodes, or the data nodes, will help maintain the actual data itself, so the actual copies of the data, and will be responsible for data access, data creation, and data deletion. So they will help with read and write operations that come in, and will create the blocks, delete the blocks, and replicate the blocks. Next slide. So in order to have a distributed file system, there has to be some method or some system in which we can break down our data in a consistent manner each time. And for HDFS, we have a block system. It's regarded as a block system. The way this is carried out is that we simply have a units, which are blocks, which are simply smaller units of data. And in Hadoop, we'd have a default size for a given block, which is 128 megabytes, and we can split our data accordingly into these chunks, or blocks, as we call them. And on the left side, as we can see, if we have a data file or a data set that is 512 megabytes in size, we'll end up splitting it equally. If we have, for the case of four, 128 megabytes for each block. And in the case on the right side, if we have an uneven or not divisible By the default size, it will simply have an extra block that will have the remainder of the file size or the residual amount. And this default size for the blocks can be changed as needed in the configuration files. Next slide. So as an example, to illustrate an example on the block system, if we have a text file or a TXT file that contains, let's say, a large amount of textual data, which is 518 megabytes in size, we will simply portion this file across 5 blocks, all in order from A to E, with E being the residual size from the split. Next slide. So another important feature of the storage system is the replication, so HDFS replication management. This feature is generally responsible for ensuring the reliability of the data by helping replicate it across different data nodes that we have in the cluster, which is how we make the system fault tolerant, highly fault tolerant. So the default replication factor in HDFS is 3. However, as we can see from this specific example, we can customize the replication factor um, by assigning different block IDs depending on our specific application requirements. And here we see that block IDs 1 and 3 have an assigned replication factor of 2. So across all of our 8 data nodes, we will only see 2 copies of blocks 1 and 3. For the others, so blocks 2, 4, and 5, they are assigned a replication factor of 3. So similarly, across all of these 8 data nodes, we will see 3 instances or 3 replicas of blocks 2, 4, and 5. Next slide. So just to further show the data replication process in action and by default, we can take a look at the right where we see the default factor value of 3 occurring. We will start off in order from blocks 1, replicate it 3 times, and then continue the same process where we have block 2, replicate it, uh, replicate it more so that we have a total count of 3, and so on and so forth for blocks 3 and blocks 4. Next slide. So now there's another dilemma that arises when we have this split of data across our Hadoop system. So since we can have a large number of machines in our Hadoop ecosystem, which is the case in most full deployment and production operations, we come to the concept of racks. A rack is simply a collection of machines that are connected together, and we can connect all of these racks together essentially via switches. And the machines in the rack are all usually stored in the same location just for security purposes and to help with data latency and different bandwidth requirements to assist in the overall system. Next slide. And now since we have different racks, we have to have a sort of rack awareness. This is proprietary to HDFS, where we want to increase the reliability and fault tolerance of the different blocks that we have. And so we want to ensure that we are not having all of our replica blocks on the same rack itself, as if the rack goes down or the specific location itself goes down, we still have our data elsewhere. So to do that, Hadoop has a unique rack awareness algorithm that helps it choose where exactly to read and write the data to assist in the trade-off that we have between the reliability, so having this data available for us when we need it, and read and writing bandwidth. So the speeds of read and writing bandwidth, as this will come with a compromise where we'll have to communicate different places to read and write the data itself. Next slide. So to take a look at the complete architecture of HDFS, we can now bring it all together and look at it in its entirety of how it works. We always have our master or name node that will manage our access to our data nodes and store it across different racks. So in this case, rack 1 and rack 2 per the diagram. And the name node or master will maintain our important metadata. And finally, we'll have replication automatically carried out as new data is added to the system with the feature of replication. Next slide. So just as a summary and recap of the important features and benefits that HDFS provides, it enables the Hadoop ecosystem to have very good fault detection and recovery. It helps it have distributed storage and processing, allows us to access files and data in a streaming manner, and almost functions as the heart of big data processing for Hadoop, so that we can process everything as a complete system. Next slide.
So I'm going to be going over the advantages and disadvantages of the Hadoop system and some examples and the reasons why it's used in industry. So, one of the main advantages of Hadoop are its ability to leverage commodity hardware, which is just known as typically like off-the-shelf kinds of hardware. So obviously the way Hadoop was made, it takes advantage of parallel processing among different machines and communication between processes. That's another advantage of Hadoop, which allows it to work with big data sets. Data locality, which is which is essentially what HDFS achieves by splitting up the data into smaller parts and then moving the application or the process to those different parts. So fault tolerance is another advantage of the Hadoop system, in the way that it's able to recover processes that go bad or have some sort of error, and continue without crashing. And scalability is another known advantage of Hadoop. But its scalability is limited to the petabytes range of data in practice. Along with the advantages, there are some disadvantages with the Hadoop system. So one is that it's mainly targeted for large scale data sets. If you use Hadoop on smaller scale data sets, you don't really see any improvement on your ability to process the data. Another somewhat disadvantage is that the Apache Hadoop system is all run in Java. So in a way, that's an advantage because Java can be run on multiple machines, but in some ways it's a disadvantage because it requires more knowledge about development in Java, since the whole framework is kind of made in Java. That's not to say that Hadoop can't be implemented in other languages, but the main open source use of it is through the Apache Java. So, and there's a very complex network infrastructure between all the nodes and switches and things like that. So having knowledge of these, the way of the network is important for being able to implement that. One major disadvantage of Hadoop is that it does not allow for the processing of real-time data, because the data has to be incorporated into the HDFS and has to be split up. So there's no real way to get real-time data processing, such as stock values or something like that, without there being some sort of a lag. And then along with that, the HDFS is all disk-based management. It's all the data is stored on the disk, whether it be across rack, every rack, every server the data is being stored on the disk. That's a disadvantage compared to some other methods that process data in the memory and which improves the speed of data processing. And then we get back to the scalability issue. And the reason why it's a disadvantage is because it doesn't scale very well above the petabytes range of data. And within the last 5 to 10 years, Google has actually retired MapReduce in favor of a newer system, the Google Cloud system, which does a better job with these larger data sets. So industry is very interested in, well, in industries where they're adopting more big data. There's still a lot of interest in Hadoop and using this system. So if we talk about anywhere from the technology industry, healthcare, logistics, academic research, many of these industries are tending towards adopting bigger data or just wanting more data. So that's basically keeping Hadoop still very popular today. So when people use MapReduce, MapReduce is able to improve a lot of typical database operations, such as sorting, searching, indexing of different indices in the database, and doing so. So MapReduce is very good at that and makes those operations very efficient, where they used to be almost impossible on some data sets. MapReduce is also able to do some more specific, application-specific types of data analysis, including modeling and data mining applications and statistical, descriptive statistics on large data sets. Some more specific examples of how these would be used in industry, MapReduce is used in industry, is, for example, so in search engine operations, such as page ranking. This was one of the first, if not the first, application of MapReduce used by Google. So in the health industry, for example, in bioinformatics, in gene and protein analysis, MapReduce has been used to help improve the processing of these kinds of things. For example, mapping genomes and running experiments on modeling proteins, which is some of the stuff similar to the work that they do to make these vaccines that they've made for COVID-19. So in transportation and logistics and supply chain management, you can imagine how complex a data might be for Amazon, which is running hundreds of millions of packages around the world. So being able to access that large amount of data and run processes on that is something achievable by the Hadoop MapReduce system. So for example, in astronomical data, it's typically astronomical data will can have be a very large database or data set, and MapReduce has been applied to that as well. So in the technology industry, there are many companies that utilize HDFS MapReduce to this day. Everything from Uber to Twitter to IBM and Facebook. They use it for different things, but essentially, you can. It's just a byproduct of the fact of working with big data, and the MapReduce system has really made that like more accessible across all these different industries. And you can see MapReduce on this graph here they show that MapReduce is, this graph was taken from a study of different companies and how important these different systems are to them. And you can see MapReduce of 45% of those companies, MapReduce was considered to be either critical or very important to their big data infrastructure. And these other examples are competitors, I guess you can say, of MapReduce, or spin-offs of MapReduce. So as I was saying, there's a lot of, since MapReduce has been made, there's been a lot of development in big data infrastructure projects. There's a lot of spin-offs made of MapReduce. There's a lot of alternatives to MapReduce. For example, Apache Spark was developed by UC Berkeley, and it does a lot of what MapReduce does, except it tends to be faster and has real-time capability. And this is because Apache Spark doesn't utilize the HDFS, but a different type of system, which allows processing to be done in memory rather than in storage. The Google BigQuery and Google Dataflow project is the successor to MapReduce in their operations. HPCC is an example of a company. How would I put that? Not necessarily licensing, but that offers big data capability to other companies willing to hire them. So they can set up they can set you up with a system like MapReduce and basically handle that for you if you're not a technically inclined company. And then Microsoft Azure is an example of similar to MapReduce for handling big data and processing big data. So I'm going to get into our MapReduce demo. So in this demo, I've set up a MapReduce system on a Mac computer of running in a pseudo distributed mode. So I'm going to go through the basic steps of what it looks like when you install it and how to do a simple example of using MapReduce, which will be a processing of a text file and counting the text in the file. And also this example is, I'm going to be showing you how you can incorporate Python written program into the MapReduce framework. So it's not going to be all in Java. So to start off, we're talking about MapReduce 3.3, which is the one I'm going to be demonstrating today. So the requirements for this demo would be you have Java 8 installed, and you'd want to download Apache Hadoop 3.3 from their website. So you need to enable SSH in your computer, and that's the communication protocol used to do all of the background work. So these instructions are more specific to Mac, as I said, and for Windows or a Linux computer, there might be differences, but I can't get into those. I wouldn't be able to get into those right now. And also, if you want to go back to this at some point, these are some resources that I found helpful for setting up this demo. So just a quick question. I'm bringing in my terminal screen. Can you guys see that?
Yes, we can see the screen. Yeah.
Okay, I'm just going to put it back to the side now. Actually, I'll bring it up here. So when you initially set up MapReduce, you want to have a SSH installed on your computer. So one way of doing that is by using OpenSSH if you don't already have that. You want to enable a passwordless access to the local host on your computer. So if I put in this command to my computer, SSH localhost, and I don't get an error, and you can see that it is successful. So, and the reason why you need that again is because in the background, MapReduce is using this SSH to do all of the background work for the data processing. So as I had said before, you download Java, and then you want to download Apache Hadoop. For this demo, I actually just uninstalled everything to do with Java, and I started from scratch, because I found that to have less conflicts. You can see an example in the top right of my screen where after I've downloaded the Apache Hadoop from the website, I just put that directory into my home directory. And you can see an example of some files that have been reconfigured in Apache Hadoop to support the pseudo distributed mode. And just in case, if I didn't mention what pseudo distributed mode is, MapReduce runs in 3 different modes. One is the single node mode, where everything is done on one process. Then there's the pseudo distributed mode, which breaks up the processing into different processes, but all on the same machine. And then there's fully distributed mode, which does the traditional MapReduce work, where it splits work up into multiple machines. So in order to configure these different modes, it's simply a matter of going into your MapReduce folder and editing certain configuration files. In this case, as I said, I edited these to enable pseudo distributed mode. If I had enabled this for fully distributed mode, I would probably have to edit some of these files for it to point at what ports on the different machines need to be open for the processes to connect when the MapReduce is executed. On the below that, you can see an example of some configurations I made in my bash profile. So I just added Java, some pointers to the Java location of Java, the location of Hadoop, and some other things that help this process. And lastly, you can see at the bottom an example of initializing the HDFS. So I'm based in this bottom command. So HDFS is the API for HDFS. And all right. So by running this command below, I'm basically formatting that. Sorry, I'm formatting the HDFS directory. So also this another tip. So I added some more pointers to run these simple commands for Hadoop. What these commands are, they basically start and stop the different processes. So you can start and stop yarn just by itself. You can stop and start HDFS by itself, or you can start all of these services at once. And I'm going to do that now, just so I see everything's working. So it looks like it successfully started all the different services. I'm going to double check by using a command JPS, which is going to show what active services there are. So you can see that I have a secondary name node, a resource manager, node manager, and data node. So, and those are some of the services that Ethan had talked about. And now they're active on my system. So one useful feature of Apache MapReduce is a web interface that you can use to see more detail about the services without having to use a terminal. So I'm going to open up another web browser and to take a look at those. Can you guys see my other web browser?
Yes.
Yeah.
Okay. Let's see. So this right here is the browser for the node manager, and it has some more details about how the system is set up currently. This browser here shows cluster statistics, how many clusters would be open and such. Right now there's none because it's not running anything and because it's not in pseudo distributed mode. So this is supposed to be my resource manager, but it's not working. So let me see. I've had this problem once before, and I had to format. Okay. Just bear with me. Hopefully I can get that working. Okay, now it's working. So this was the node manager, the cluster statistics, and this is the resource manager. So you can see just some kind of background information about what's going on here. More importantly, for the purposes of this demonstration, they have a file browser. You can browse the file system here pretty easily. So you can see I had to format the HDFS because there was some sort of error. And now that I formatted it, it's completely empty. So there's no data available. So I'm just going to put that to the side. And so after you've set up HDFS and when you see that all of your services are active and you get access to these things, you're probably good with that. And the next step would be to form a MapReduce program, load your data, and execute the process. So this is an example of the MapReduce program that I developed in Python. So actually I have it here too. I'm not sure if it's easier to read. I developed a mapper and a reducer, and both of these are targeted towards the word counting problem. So we take a text file, and for every word in that text file, we want the end in the end result. We want to know how many times does this word appear in the text file. In order to do this with a Python program or any other kind of program that's not in that's not going to be intrinsic to Java and the MapReduce. We're utilizing something called the MapReduce streaming API, which basically allows, by using the streaming API, it basically allows you to have any process and pipe the data to Hadoop. And if it's formatted the right way, Hadoop will do the job with it. So in this case, in my mapper, so remember that the mapper is taking chunks of the data and then decomposing it into some smaller parts and then sending that to the reduce process. And this is done through the system, the standard input and the standard output with the sys library. And so I'm just doing some basic text
Daniel,
processes. Yes.
sorry to interrupt you. I think for the mapper and the reducer, the basic concept you already present to us, we are aware of this basic concept. I think we can go directly to the demo part. If we have any question, then we can go back to the code part. What do you think?
All right, sure thing.
Yep.
So after formatting your HDFS, I'm going to make a new directory in the HDFS. It's just going to be my name, a user. And then I'm going to copy the data from my project directory into HDFS. And because I'm on a Mac, I'm also going to delete some files that are associated with the Spotlight. And I'm going to double check on this file browser that my directory has been created. And if I go find myself, and then I find my example, and I can see that my example is a text file. So now I'm going to execute a MapReduce process. So what you're seeing here is I'm using the Hadoop, I'm accessing Hadoop and I'm pointing it to the Hadoop streaming API. And through the API, I'm giving it a pointer to the files of interest. So it's going to be my mapper and my reducer. And I'm specifying that what my mapper is and what my reducer is. I'm telling it what is the input of the data. So right now it's just one text file, but if I wanted to add 1 million text files, they could all be under this directory examples. And I'm telling it where I want my output to go inside of HDFS. So now MapReduce is going to process this text file with the MapReduce system is going to determine how many processes need to be opened. It's going to determine how many mappers and reducers are going to be spawned and linked together to process the data, and all that happens in the background. So there's no need to specify that, although it's definitely possible to specify in more detail what processes you want to be done. So now it looks like everything's done. So I'm going to go back to my directory. So now I have an output file in my HDFS directory. And if I access that, it looks like everything worked out great. And if I look at the data that was generated, you can see here that there are different words or text, pieces of text that have been indexed from the text file. For example, you can see that the word Alice with a comma appeared or just Alice appeared 4 times. And the word all appeared 164 times. So that's a very short example of how to run MapReduce in a pseudo-distributed mode.